Good morning. Today we are going to talk about the subgroup of the additive group of integers. If you see, from my experience, what I find is that many students know about finite cyclic groups, etc., but they are ignorant of additive subgroups of the additive group of integers. And this is very interesting because it has a lot of kind of overlap with number theory as well as ring theory when you are going to learn ring theory. And so we will stick to only additive group of integers. Okay, I hope you appreciate this lecture, and there will be a lot of subtle points which you will learn at the end. Okay, now let's share the screen. Yeah, so there are two ingredients. The first ingredient is the so-called well-ordering principle. What does it say? Suppose A is a non-empty subset of Z plus. For me, Z is the set of integers. Z plus is all natural numbers union 0. That is all non-negative integers. Okay, suppose this is a non-empty subset of Z plus, then there exists an M in A so that for all x in A, M is less than or equal to x. That is, one usually says there exists a unique least element. Unique least element. That is the smallest element in A. This is intuitively obvious, but it's one of the so-called Peano's postulate, at least for the set of natural numbers. Okay, we extend it to Z plus. Okay, right. This is the first ingredient. Second ingredient is the so-called division algorithm. Okay, what does it say? Suppose A is a positive integer and B is any integer, then it says there exists unique QR in Z with the following two properties. So that one, B is AQ plus R, and 2, okay, this R is restricted. Okay, and the uniqueness is subject to these two conditions. That is, if I write B equal to AQ1 plus R1, then Q must be Q1, R must be R1. Okay, these are the two ingredients which are going to talk about. Okay, we are going to exploit. Okay, so now let's look at, suppose, let me look at Z as the additive group of integers. Let H be a subgroup of Z, G. Okay, now if H is trivial, there is nothing to prove. Okay, then we know this. Okay, there is nothing for us to investigate. So let us assume the subgroup H is non-trivial subgroup, non-identity subgroup, right? Then there exists at least one, let us say A in Z, A not equal to 0, and so that A is in H, right? H is a subset of Z, and if this is not equal to 0, it contains at least one non-zero element. Now since H is a subgroup, then we know both plus or minus A are in H, and remember A is non-zero, therefore one of them is positive. So without loss of generality, let's assume A is positive. You understood that? Okay, right. This is we used here the fact that H is a subgroup, right? Next, now let us look at H plus to be the set of all x in H. Okay, that is such that x is positive. So remember, this case 1 is over. I am looking at case 2. Okay, therefore H is non-zero, therefore there exists, or okay, this is non-empty. Why is non-empty? Because we know there is at least one element, non-zero element, and hence plus or minus of that non-zero element will be positive. Therefore this is non-empty. Now notice that H plus, okay, is a subset of natural numbers now. Yeah, and this is non-empty because A belongs to that. Therefore by well ordering principle, okay, let there exists an n okay, in H plus, such that n is the least element of H plus. Yeah, is that clear? All right, now something interesting happened. Now suppose, let us call this n. Suppose I have an element, I'll call it B in H, right? Now B is here and n is here. N is positive, okay? Remember, n is positive integer, right? Natural number. Now, can I not apply the division algorithm? Of course I can do that. So what will I have? I will have B equal to n times q plus r, where 0 less than r less than or equal to n minus 1 by division algorithm. Right? Yeah? Alright. Now let's look at, what do you know about B? B is in H. What do you know about the element in Q? Remember, n is an element of H plus and hence is an element of H. Therefore, it's a multiple. That is Q plus Q plus Q n times. Okay. N could be negative also, but doesn't matter. Okay. In that case, it's minus Q minus Q minus Q minus n times. Are you following? If it is minus this, that only says minus Q minus Q minus Q. This 5 times. Okay. So this is also an element of H. This is an element of H. Therefore, what do I conclude? Therefore, R, which is equal to B minus NQ, this is also an element of H. Because why? We are using the subgroup property. Remember, if H is a subgroup in the multiplicative notation, if A and B are there, then you know that, okay, B A inverse, R A inverse B, etc. They are all in H. Okay, I am using that in additive notation. Therefore, this is in H. Something interesting happened. How many of you can see that? So I use division algorithm. So there is something about R. What is R? R is between 0 less than or equal to R less than or equal to n minus 1. Do you understand? Now, can R be positive? Can this happen? Suppose this happens. Remember, R is an element in H and R is also positive, but R is strictly less than n. But what was my hypothesis about n? N is the least positive element in H. It is the least element in H plus and hence it's the least positive element in H, because H plus is set of positive elements. Do you understand? Therefore, what do I conclude? Yes? Did all of you get the answer? Yes. Therefore, we conclude, yeah, okay. If so, then R is this is a contradiction, because n is the least positive element in H. Therefore, I conclude R must be 0. Do you understand? Fantastic. So, what do you think I have concluded? Therefore, I start with an arbitrary element B in H, given any B in H, then I return by division algorithm NQ plus R, but R is 0, therefore it is n times Q. Right? So that means if at all B is any element in H, it has to be a multiple of n. Do you understand this? Do you appreciate? So what you have concluded is, if B belongs to H, then B is a multiple of n. What is n? Remember, you always keep that in mind. N is the least positive element in the subgroup H, and we are assuming H is non-zero. Keep that in mind. All right. Therefore, let's look at, give a name. Let Hn be equal to n times z. This is set of all k times n, where k varies over all z, all multiples of n. Set of multiples of n. Yeah. So what you have shown is my subgroup H is a subset of Hn. That's all I have shown, right? Any element B in H is a multiple of n. Therefore, all I know is this. Okay. But I want to say the other way inclusion is also true. Why? Because you start with any element here, it is of the form k times n. Since n is in H, k times n also in H. Therefore, H equal to Hn. Have you understood? So what you have done, so therefore what you have proved is the following result theorem. If H is a subgroup of Z plus, then there exists a unique n in Z plus such that H is n times Z, or it is same as Hn. We will call it as Hn. Yeah, right. Have you understood? Pause, review, and then proceed. So let us think carefully. What do you think we have proved? We have proved, therefore, for every natural number, for every non-negative integer n, I have produced a subgroup Hn, which is n times n, right? And any subgroup H of Z plus is of this form. Okay, that means there exists a unique n that the H equal to Hn. Okay, these are all we have proved. There is a very natural question I could ask. What is the very natural question I could ask? Suppose I start with m and n in Z plus, and suppose m is not equal to n, are these subgroups distinct or the same? Can I conclude that? You understand that? Yeah, that's very easy. And unfortunately, people believe it's obvious. It's of course easy, but then all this kind of thing you should learn how to check very carefully. Now let us assume, since m is not equal to n, so one must be strictly less than the other. So let me assume m is strictly less than n. Suppose m equal to 0, then n is not equal to 0. Therefore n belongs to Hn, but n is not in H0, which is 0 times Z, which is 0. Do you follow that? This is not here. Yeah, therefore if m, okay, if m is 0 and m is less than n, 0 less than n, then H0 is distinct from Hn for every n greater than equal natural number. Do all of you agree with that? Yeah. So let me assume, therefore I am left with the case 0 less than m less than n. Then I want to know whether Hm is not equal to Hn. Yeah, okay, but that's again easy. Why? Can somebody say why? Think about what is the relation of the natural number m to the subset, to the subgroup Hm, and what is the relation of natural number n to the subgroup Hn. Always think about that. Okay, m is the least element. This is the least element in Hm, right? So if Hm equal to Hn, then m must be in Hn, right? But n is the least element in Hn, when I say least element, least positive element. Okay, m, if m belongs to Hn, whereas n is the least positive element, therefore m must be greater than or equal to n, but that's a contradiction. Do you follow that? Therefore what we have shown, if m is not equal to n, all these subgroups, what are the m and n? They are in Z plus. Okay, Hm is not equal to Hn. Pause, review, proceed. So we can strengthen our earlier theorem. You see, notice that earlier theorem, what did it say? It said simply, for each, if H is a subgroup, okay, then it must be of the form nz, where n is the least non-negative element in H. You understand? Right. Now what are we saying? All these subgroups are also distinct, right? Therefore we can conclude, strengthen the theorem. Therefore the only subgroup, the only subgroups of Z plus are of the form n times Z, which is Hn for n in Z plus, and further they are all distinct. Furthermore, they are all distinct. What does it mean? If m and n are in Z plus and m is not equal to n, then Hm is different from Hn. Okay, this is the final result we have proved. Okay, pause, review, proceed. Okay, now let's go to the next question. Okay, the next question is the following. You know, if G is any group and H1, H2 are subgroups of G, then you know H1 intersection H2 is a subgroup of G, right? Now let's try to see what it means for our subgroups in Z. Okay, you will be very thrilled to see a lot of very interesting things happen here. So let us assume H1 equal to Hm. This, okay, sorry, let G equal to Z plus, and let us look at one subgroup to be Hm, the other subgroup to be Hn. This is m times Z, this is n times Z, right? Now I want to know what is Hm intersection Hm. This will be a subgroup, I know. Yeah, think carefully. Yeah, this will be a subgroup because intersection of subgroups is a subgroup. But notice that this being a subgroup of what? Z plus. But I know all the subgroups of Z. What do I know? They are of the form some Hk where k is in Z plus, right? Therefore there exists a unique k so that Hm intersection, let me write it carefully. Okay, it must be a subgroup which is multiples of k. Do you understand that? Yeah, right. Yeah, okay. Now let's try to understand what it really means. Suppose I have an x, okay, or let us say x in Z that belongs to Hm intersection Hm. What does that mean? That means x is a multiple of m, and similarly for the same reason it's a multiple of n. You understand? Yeah, right. Now just think again carefully. In particular, if these two are equal, this subgroup Hk contains k, therefore k must be in Hm intersection k Hn. Therefore in particular k must be a common multiple of m and n. You agree? Now, so if you are high school, it will tell you or even school, the moment you think of common multiple, what do you think you will think of? Yeah, therefore every element in Xm intersection Xn must be a multiple of a common multiple of m and n. But then let's look at Hm intersection Hn, that is Hk. Therefore k itself is a multiple of m and n. But if any x is in intersection of Hm intersection Hn, x is a multiple of m and n. But x belongs to Hk, therefore x is also a multiple of k. Do you understand? But k is already a common multiple of, sorry, m and n. So do you have any guess what k should be? Yes, there is obvious guess, right? I would expect my k to be L, where L is the least common multiple of m and n. Yeah, do you agree with that? This is a guess. We still have not proved it. Yeah, let us look at. Now that's almost obvious. Again, m and n are non-negative. Okay. Remember, we can again assume that none of them is 0. Neither m is 0 nor n is 0. Right? If one of them is 0, it will be the other subgroup. Do you follow that? So let us, to avoid trivialities, let us assume m is also not equal to 0, n is also not equal to 0. Therefore, m and n belong to natural numbers. Okay? Right. Let's come to this. So what do we have is my k, this is my guess. Now let me strike this L. I will stick to L. Suppose L is the least common multiple. Since therefore it's a multiple of M, therefore L belong to HM. And it's a multiple of N, therefore it belong to HM. Right? Agreed. You follow that? Yeah? Okay. You follow that? Okay. Now this is in HK. What do I know? Okay. This is my guess. Okay. K is what? Please don't get confused. HM intersection Hn is a subgroup. Any subgroups of the form HK. This K is what I am trying to point out. You understand? On the way, we thought about, analyzed, and we thought my K may be L. So at present, I do not have any idea about the relation between K and L. So that's why I have to write it. But what I know is L being common multiple of M and N, L belongs to HM and intersection Hn. Therefore, it belongs to HL. Therefore, L must be a multiple of HK. Yeah? Do you follow that? Yeah. So what have we shown now? Now, if X belong to HM intersection HN, which is equal to HK, then I know X is a common multiple of M and N. Therefore, I know X itself must be a multiple of L, because do you understand? Since L is the least common multiple, I am using your basic idea of number theory. If L is a common multiple, okay, then what do I know? This X is a multiple of M and N, therefore L must divide 6. Yeah. Now notice that K also belong to HM intersection HN. Therefore K must also be a multiple of L. But L is a multiple of K. Both are positive integers, right? So L and K both are in N, are multiples of each other. Therefore L must be equal to K. Okay, this again requires a proof. If you are a BSc student, it will be nice to think of such things, how to prove that. Because how do I know L is a multiple? So let us call it some R times K, and K is a multiple, therefore let us say S times L. Therefore this is R times S times L. Therefore what do I have? L into 1 minus Rs equal to 0. Notice that these are all, where is R? This is in N. Where is S? This is also in N. Therefore L into this is 0, right? The product of two, remember L is also positive. This is this has to be 0, right? What does it mean? This implies 1 minus Rs must be 0. This implies Rs must be equal to 1. Remember, what do I know about R and S? They are natural numbers, but their product is 1. Therefore R equal to S equal to 1. That means L equal to K. Yeah, please pause, review and proceed. So you saw that. So do you see something interesting? We are thinking about additive subgroups of Z, but intersection of subgroups is a subgroup we know, but in this particular case the intersection of HM and HN is the subgroup generated by, that is HL, where L is the least common multiple of M and N. Okay, so what have you shown? So we have shown that. So this is the theorem you proved. Okay, assume M and N are natural numbers, then HM intersection HN equal to HL, where L equal to LCM M and N. Yeah, right. Okay, So pause, review, proceed. We now go to the next step. Okay, let me take HM and HN. Okay, I want to add. What does this mean? This set of all elements of the form x plus y, where x is in HM and y is in HN. I want to know that it's a subgroup of Z plus, of course. That's very easy because I have x1 plus y1, okay, minus x1 minus x2, sorry, x2 minus y, x2 plus y2, okay. One element is x1 plus y1, other element is x2 plus y2. You follow that? And x1 x2 are in HM, y1 y2 are in HN. Do you follow that? But this is nothing other than x1 minus x2 plus y1 minus y2. And where are h1 x1 x2? They are in HM. HM is a subgroup, therefore this is an element of HM. And for a similar reason, this is an element of HN, therefore this belongs to HM plus HN. These are the forms of x plus y, where x is in HM, y is in it. Therefore this is a subgroup. Do you understand that? Therefore what do you concluded? HM plus HN is a subgroup of Z plus. Okay, so therefore I know that it must be HM plus HN should be of the form, okay, HK for some K. Okay, there is a unique K in Z plus, so that this must be equal to HK. Yeah, again let me assume M and N is not 0, N is not 0, because if one of them is 0, let us say xm is 0, then it consists of 0 plus y, y is in HN, therefore it's HN only. Do you follow that? Yeah, if M is 0, then HM plus HM is HN. Okay, therefore we can avoid this case. Okay, so we will assume M is not equal to 0 and N is not equal to 0. That's a case which is interesting. Okay, so I know this will be a subgroup. Okay, HM plus HN is a subgroup, therefore it must be of the form HK. So I want to know what is K, right? Now think carefully, so you should develop intuition. In the last case, what did we find? HM intersection HN, okay, was some HL where L is the least common multiple of M and N. You follow that? Yes or no? Sure? Very good. So this L has something to do with M and N. Yeah. Similarly, I can expect in this case HM plus HN equal to HK. This K must have something to do with M and N. Make a wild guess. Yeah. How many of you get it? You may be wrong. It doesn't matter. Say that. I guess this is my guess. K is GCD of M and N. This is what you have to check. You follow that? Yes? Okay. Now let's go slow. Let's argue. Now suppose I have HM plus HM equal to HK, right? So start with any element X in here. Okay, or call it Z. Okay, Z here. Then Z is of the form X plus Y. That is going to be some multiple of, okay, R times K. Right? We still have to find K. Okay, please understand, I do not know K. It's my guess. I don't want to verify. I just want to kind of derive the result. Okay, I can take this and then verify, but that's not our way of doing things. Okay, take X plus Y. This is an RK. Yeah, right. Now what can you conclude? Yeah. Now notice that this K, right, this K must be an element of here, right? Therefore there exists X and Y, so that X plus Y equal to K in particular. Okay, given K must be sum of two elements from Hm plus Hn. Do you all of you agree with that? Okay, good. So what can you do that? So any element here is divisible by k. Any element in Hk is divisible by k. Therefore, x plus y must be divisible by k. That's what we wrote. Yeah. Then how do you conclude common divisor? We made a guess. So can you say this k must be a common divisor of this? Come on. See, it takes time, right? Okay. If the teacher does, it look easy. See, what I can do is I can take m in Hm plus Hn, where that is m equal to m plus 0. This is x plus y, where x is in Hm, y is 0. Do you understand? Therefore, m itself in Hm plus Hn, but that is by assumption Hk. Therefore, k is a divisor of m. And similar reason, k is a divisor of m. Therefore, k is a common divisor. Do you understand this? I just was playing with you for a while just to see. Okay. So notice that in Hm plus Hm, m is also an element, n is also an element. Because I only have to take the other element x plus y, one of them to be 0. And hence any multiple of m will also be there. No, therefore Hm is contained in Hm plus Hn. And similarly Hn is also contained in Hm plus Hn. Is that clear? Yeah. So what you have found is it's a common divisor. Right? Now we are through. Therefore you start with any element x plus y in Hm plus Hn. Therefore this is something like some r times m plus s times n, and therefore since k divides m, k divides n, k divides m plus 1. So we know that. That's fine. Right? Okay. Now let us look at G to be the greatest common divisor of m and n. Yes? Yeah? Okay. Now what do you know? Therefore what do I know is G is a greatest common divisor and k is a common divisor of m and n. Therefore what is the relation between k and G? Right? K must be a divisor of G, or you can also say k is less than or equal to G. Okay, because it's the greatest common divisor among all positive divisors. G is the greatest and k is a common divisor, remember, and we assume k is not equal to 0. K cannot be 0 because m is not 0, n is not 0. Therefore k cannot be 0. If k is 0, this will be 0 subgroup, right? Therefore k is also positive, right? Therefore there are two positive things, k and G, both are common divisors of m and n, right? Whereas G is the greatest common divisor, therefore k must be less than or equal to G. Do you follow that? Yes? Okay. Now what do you conclude? So what have you shown? So we have shown that Hm plus Hn equal to all multiples or k times z. Okay, that is Hk. Right? So we have known that, and suppose G is a GCD of m and n. Right? Okay. Now what do you conclude? So G is the greatest common divisor, right? Very good. Now let's look at. Therefore, G divides any element x plus y in H. Okay. Remember, K is an element here because K. is we are assuming equal to kz, hk. Therefore, k must be an element of this. So, in particular, g must divide k. Right? Notice that both are non-negative. So, I know k divides g. K is less than or equal to g. I already concluded. But whereas g divides k, but both are natural numbers. Therefore, g must be less than or equal to k. So, these two implies k must be equal to g. Yeah? So, what have we shown? We have shown that mz plus nz equal to dz, where d is the greatest common divisor of m and n. Right? Okay. Let us observe one or two more things. Now suppose you must have heard the word m and n are co-prime, that is GCD of this is equal to 1. Yeah, okay. If GCD of this is equal to 1, then what is mz plus nz? That is 1 times z, but that is z. So what does this mean? If GCD of f and n are 1, then there exists, okay, r and s integers such that m times r plus n times s or rm plus sn, whatever you want to call, this equal to 1. So this is called Bezos identity. Yeah. All right. Do you follow? Okay. Right. Now there is one more thing I would like to say. Suppose p is a prime number. Okay. Then let's look at p times z. Okay. And suppose there is a subgroup h of z plus, so that pz is contained in h. What can you conclude? Remember, therefore, pz is contained in some, let us say, n times z. Right? What does it mean? Therefore, p belongs to nz. Therefore, n divides p. You understand? Yeah, this means p belongs to nz. Therefore, n divides p. Lord, p is a prime. Therefore, what do I know about n? N must be either 1 or equal to p. Therefore, the moment you say pz is contained in h, then h is either z or h is pz itself. Yeah? This is just an observation. Now let's look at the next notion of cosets. Okay. Now let h equal to hn equal to n times z, and assume n is natural number, n times z is a subgroup of z. Okay. Then what are the cosets? Notice that this is an infinite group, this is also an infinite group. Okay. What are the cosets? Cosets are the form a plus n times z, where a is some integer. Right? Remember, if h is a subgroup, gh is, these are the cosets. Right? Now something very interesting happens. Suppose I write a as some n cube plus r, where 0 less than or equal to r less than or equal to n minus 1, using division algorithm. Okay, then something very interesting happens. What happens? Okay, can somebody tell me? You remember, when are two cosets equal? AH equal to BH? If A inverse B or whatever you want to call, okay, or A B inverse, that must be in H. Because I am working with a competitive group, so let me just use it. Okay, you understand this? AH1 must be equal to BH2, therefore H1 equal to A inverse BH2. Yeah, therefore A inverse B will be some multiple. Okay. You understand? Now, right, now let's look at A minus R. A minus R n times Q. This is an element of nz, that is our subgroup Hn. Therefore, the coset defined by A plus nz must be same as the coset defined by R plus nz. Okay, pause, review, proceed. Make sure you understand. So how many cosets are there? See, typically for every A in Z, I can construct a coset, right? And there seem to be infinitely many cosets, but what happens is, as sets, they all coincide. Most of them coincide. I have only finitely many cosets, that is 0 plus nz and 1 plus nz and n minus 1 plus nz. These are the only n cosets of the group of nz in Z. And how do elements of this, let us start with J here. How do the elements of that comes? It is J plus n, J plus n plus n, that is 2n, and so on. Here J minus n, J minus 2n, etc. This is your J plus nz. Notice that this is, so the coset is nothing other than an arithmetic progression going both sides. Okay, two-sided arithmetic progression. Start, the initial thing is J, starting with J, and common difference n. Do you follow that? Yeah. And not only that, this is nothing other than what you call, in number theory, you call it the congruence class. You denote it by J bar. This is the congruent class. Okay. There. This is J plus nz. So these are the cosets. Right? Okay. So these are the things I wanted to talk about. Think about carefully. Okay, you will understand better. Let's look at what you achieved. The aim of this lecture was to study the subgroups of the additive group of integers. And as I observed, we needed two facts. One is well ordering principle, the other one is division algorithm. Right? Now go through the proof, you can understand line by line. That's not a problem. But try to learn to think deeper. Ask what are the things we really use. Was there any trick? See, we are allegedly looking at the additive subgroups of Z plus, but all our proofs, if you notice, use multiplicative structure of Z also, right? There was another binary operation, namely multiplication on Z, and that came in the form of division algorithm, and we have to use that. Okay, this is something very, it should interest you, right? Do you understand? And you will see that no textbook, no author will say such things, teacher. So that's something very surprising. I needed multiplicative structure to deal with the additive subgroups of Z. Okay. And if at all you are learning, or you will learn ring theory, you will learn a lot of things like UFD, unique factorization domain, principal ideal domains, Euclidean domains, right? In which of this category of rings this similar analogous results hold? Try to think. Okay, that will be a good exercise for you. Yeah, I hope you appreciate this. So even that's some small things, there are a lot of things we can learn. Yeah, so it's up to us to think carefully. It's not simply mere understanding. Reflect upon, ask yourself question. Even if you don't get answer, don't worry, please do that. You'll enjoy. Okay, I'll stop the lecture. Take care, stay safe.